Hello everyone. Welcome to this video series on the complete design of an H-bridge inverter board. In this series, we are not just looking at theory or simulations. We are going to design, build, and test a real, high-power inverter hardware, step by step. We will begin with the system-level specifications and move on to the schematic design, where we will carefully select and justify every major block, including the IGBTs, gate drivers, isolation strategy, and protection circuits. Next, we will focus on PCB design aspects, especially those that matter in power electronics, that is, current loops, creepage and clearance, gate drive routing, grounding, and noise control. A part of this series will cover IGBT selection and thermal design, including how to choose the right heat sink, how to estimate power loss, and how mechanical mounting affects reliability. We will also design the isolated power supplies required for gate driving and explain the working of isolated gate driver ICs in detail, why isolation is required, how it improves safety, and how it prevents control side noise. On the control side, we will generate PWM signals using an STM32 microcontroller and discuss timing, dead time insertion, and safe switching practices. Finally, we will move to real hardware testing, connecting the inverter to a 1 kW load, capturing voltage and current waveforms on a digital storage oscilloscope, and analyzing switching behavior, output quality, and performance. By the end of this series, you will have a complete, practical understanding of how an H-bridge inverter board is designed, built, and tested in the real world. So, if you are a student, researcher, or practicing engineer in power electronics, this series will give you insights that go far beyond textbooks. Let us begin with the system overview of the H-bridge inverter board. This inverter is designed around a DC bus voltage of 400 volts. With this DC bus level, the inverter is capable of generating a 230 volt AC output, which is suitable for most single-phase AC loads. The designed load capacity is 3.3 kilowatts, which places this inverter firmly in the high-power category. This means special attention is required in component selection, PCB layout, thermal design, and protection, topics that we will cover in detail in this series. The inverter operates at a switching frequency of 20 kHz. This frequency is a practical trade-off between switching losses, output waveform quality, and filter size. For the gate drive circuitry, a low-voltage DC input of 12 volts is used. This 12-volt supply is converted on the board into isolated power supplies required for safe and reliable gate driving of the IGBTs. The logic-level control inputs are 3.3-volt compatible, making the board directly interfaceable with modern microcontrollers such as STM32 devices, without the need for additional level shifting. The DC bus input terminals and the H-bridge output terminals are implemented using 3.5 mm bulate connectors. These connectors are selected to handle high current while providing reliable and low-resistance connections. For driving the IGBTs, the board provides asymmetric gate voltages of plus 15 volts and minus 9 volts. This ensures strong turn-on, fast turn-off, and improved immunity against false triggering due to Miller effect. Thermal management is also an integral part of the system design. A dedicated connector is provided to power a 12-volt BLDC cooling fan, which is mounted on the heatsink to maintain safe operating temperatures under high-load conditions. This system-level architecture forms the foundation of the inverter design. In the upcoming sections, we will break down each block, starting from schematic design, moving through PCB layout, and finally validating the design through full-power hardware testing. Let us now examine the power circuit of the H-bridge inverter shown on the screen. The inverter operates from a 400-volt DC bus, which is applied to the board through connectors J5 and J10. These connectors form the HV+ and HV- rails, supplying energy to the entire power stage. The inverter itself is implemented using a full H-bridge topology, built around 4 IGBTs, labeled Q1 to Q4. The AC output is taken from the midpoints of the two half bridges and brought out through connectors J8 and J14. By appropriately driving the gate signals, an alternating voltage waveform is generated across these output terminals. Across the DC bus, We have decoupling capacitors C1 and C2 each rated at 220 nanofarads and 630 volts. These capacitors are placed very close to each half-bridge section, which is extremely important in high-frequency inverter design. Their role is to absorb high-frequency switching currents, reduce voltage overshoot caused by stray inductance, and keep the DC bus impedance low during fast switching transitions. Now let us look at the IGBT selection, which is a critical design decision in any high-power inverter. The device used here is the FGH60T65 SQD, a 650-volt field-stop trench IGBT. The 650-volt collect emitter rating is chosen deliberately. With a 400-volt DC bus, hard-switched inverter designs typically require a safety margin of 1.5 to 2 times the bus voltage to safely handle switching transients, parasitic inductance spikes, and any regenerative energy from the load. A 650-volt device gives us a margin of about 1.6 times the bus voltage, which is an excellent balance, safer than a tight 600-volt part, while avoiding the higher losses and cost of a 1200-volt device. From a current handling perspective, the FGH60T65 SQD is rated for 120 amps continuous at 25 degrees Celsius case temperature, derating to about 60 amps at 100 degrees Celsius, which is a realistic operating condition once the heat sink is active. For a 3.3 kilowatt inverter delivering 230 volt RMS, the output current is roughly 14.3 amps RMS at unity power factor. In a single-phase H-bridge, each IGBT conducts for roughly half the cycle, so the average current per device is in the 7 to 10 amp RMS range, with peak currents around 20 amps for a sinusoidal waveform. This means the devices are operating well below their thermal current limits, giving us 2 to 3 times headroom, even under continuous full-load operation or mild overloads, a key factor for long-term reliability. Efficiency is another major concern at 3.3 kilowatts and 20 kHz switching frequency, so let us briefly look at losses. Starting with conduction losses, the typical VCE, SAT, of this device is about 1.6 volts at 60 amps, increasing slightly with temperature. At our actual operating current of 10 to 15 amps, the saturation voltage is lower, typically in the 1.3 to 1.5 volt range. With 2 devices conducting at any instant in the H-bridge, the conduction loss per device is only about 5 to 8 watts, resulting in a total bridge conduction loss of roughly 20 to 30 watts. At 20 kHz, switching losses become more significant. The FGH60T65 SQD is a 4th-generation field-stop trench IGBT, optimized specifically for low switching losses at medium frequencies. Although the datasheet gives switching energy values at much higher current levels, our operating currents are significantly lower, so the real switching energy per transition is correspondingly reduced. In practice, switching losses remain well within manageable limits with proper gate drive and layout. When we combine both conduction and switching losses, the total power loss of the H-bridge remains under roughly 100 to 150 watts, allowing the inverter to achieve efficiencies well above 95%, which is excellent for this power level. Finally, thermal management is addressed by mounting all IGBTs directly onto a heat sink. A thermal pad is placed between each device and the heat sink, providing electrical insulation while maintaining good thermal conductivity. This ensures safe operation, controlled junction temperature, and long-term reliability under continuous high-power operation. This completes the explanation of the inverter power circuit. In the next section, we will move on to the gate drive circuitry, where we will see how these IGBTs are driven safely using isolated supplies and controlled switching. Let us now look at the gate driver circuit for one-half bridge of the inverter. At the heart of this circuit is the 2ED3146MC12L isolated gate driver IC, labeled as U4. This device provides two independent isolated gate driver channels, making it well suited for driving the high side and low side IGBTs of a half bridge. On the control side, the gate driver is powered from a 5-volt logic supply, connected to the VCC1 pins. The in A and in B pins receive the PWM control signals DRVA and DRVB from the microcontroller. These inputs are 3.3 volt compatible, allowing direct interfacing with STM32 class controllers. The GND1 pin forms the logic ground reference, and a local decoupling capacitor C5 is placed close to the IC to ensure a clean and stable supply for the logic section. The enable pin, EN, is tied to the 5-volt supply, which keeps the gate driver active. The dead time control pin, DT, is connected through resistor R1, allowing controlled dead time insertion to prevent shoot-through in the half bridge. Now moving across the isolation barrier, we enter the power side of the gate driver. Each gate driver channel has its own isolated power supply rails. For the upper device, the rails are labeled +15V_A and -9V_A, and for the lower device, +15V_B and -9V_B. Using asymmetric gate voltages is a deliberate design choice. The +15 volts ensures strong and fast turn-on of the IGBT, while the -9 volts during turn-off improves immunity against false turn-on caused by Miller capacitance, especially at high dV/dt. Local decoupling capacitors, such as C10, C11, C12, and C13 are placed very close to the gate driver supply pins. These capacitors provide the high peak currents required during fast switching and maintain low impedance on the isolated supply rails. The gate outputs, labeled OUTA and OUTB, drive the IGBT gates through gate resistors R3 and R9, each of 3.3 ohms. These resistors control the gate charging and discharging current, allowing us to fine-tune the switching speed and reduce ringing, overshoot, and EMI. The gate signals are finally routed to the power stage as gate_A and gate_B, corresponding to the upper and lower IGBTs of this half bridge. A similar, identical gate driver circuit is used for the other half bridge of the inverter. In the next section, we will look at how these isolated gate drive supplies are generated. Let us now look at how the isolated power supplies for the gate drivers are generated. All the gate drivers in this inverter require independent, isolated supplies with asymmetric voltages of +15 volts and -9 volts. This isolation is essential to maintain galvanic separation between the control electronics and the high-voltage power stage and to ensure safe, noise-immune operation. At the heart of the isolated supply generation is the 2EP130 driver IC, labeled as U2. This IC operates from a 12-volt input supply, which is applied to the VDD pin. Local decoupling capacitors C8 and C9, 100 nanofarads and 10 microfarads are placed close to the IC to provide a low-impedance supply and handle switching currents. The driver IC includes several important control pins that allow fine-tuning of the isolated power supply. The OC set pin is used for overcurrent set input. This pin allows us to define the maximum primary side current, protecting the transformer and the switching device inside the IC from overload or fault conditions. The FREQ or BYP pin is used for frequency adjustment. By selecting the appropriate resistance on this pin, the operating frequency of the driver is set to match the characteristics of the isolation transformer. The DC pin is used for duty cycle adjustment. By carefully controlling the duty cycle, we are able to generate asymmetric secondary voltages, resulting in the required +15 volt and -9 volt outputs after rectification and filtering. This technique avoids the need for separate converters and allows both gate drive voltages to be derived from a single isolated transformer. The figure given shows the resistor adjustment table from the data sheet of the isolated power supply driver. The resistor values used in our design are highlighted in the table. With these selected resistor values, the converter operates at a switching frequency close to 80 kHz and a duty cycle of approximately 38%. An operating frequency of 80 kHz is well suited for the selected transformer core, and a 38% duty cycle produces the required asymmetric gate drive voltages of +15 volts and -9 volts. The driver IC produces two complementary outputs, which excite the primary winding of the isolation transformers. Each isolation transformer is an EE16 ferrite transformer, selected for compact size, good magnetic coupling, and suitability for high-frequency operation. These transformers provide galvanic isolation and allow the generation of multiple independent secondary supplies. On the secondary side, the transformer outputs are rectified using Schottky diodes, chosen for their low forward voltage drop and fast recovery. Filtering capacitors smooth the rectified voltages to produce stable plus 15 volt and minus 9 volt rails. By using independent isolated supplies for each gate driver channel, the design minimizes common mode noise, avoids ground loops, and ensures robust and consistent gate drive performance, even under fast dV/dt conditions. Let us now look at the auxiliary interfaces and low-voltage power section of the inverter. On the left side of the schematic, we have the PWM control input connectors, labeled P1 and P11. These connectors bring in the gate drive control signals from the controller, such as an STM32. Signals DRVA, DRVB, DRVC, and DRVD correspond to the 4 switches of the full H-bridge. Each of these control inputs is provided with an external 470 ohm pull-down resistor to ground. Although the gate driver IC already includes an internal pull-down resistor of about 150 kiloohms, this value is relatively high. With long signal wires running from the STM32 to the gate driver board, these high-impedance inputs can easily pick up electromagnetic interference generated by the high dV/dt and high dI/dt power switching in the inverter. Under such conditions, false triggering of the gate driver can occur. By adding a low-value external pull-down resistor of 470 ohms, the input impedance is significantly reduced. This makes the control inputs much less susceptible to noise pickup, improves immunity against EMI, and ensures that the gate driver inputs remain in a well-defined logic state during resets, startup, normal operation, or cable disconnection. Moving to the top center of the schematic, connector P2 provides a dedicated 12-volt output for a cooling fan. This connector supplies power to a 12-volt BLDC fan mounted on the heatsink to provide forced cooling for the IGBTs during high-power operation. On the right side, connectors J1 to J4 are 4 mm mounting holes used for mechanical fixing of the PCB. These mounting points ensure proper alignment, vibration resistance, and reliable thermal contact with the heatsink assembly. At the bottom right, we have the low-voltage power regulation section. A 12-volt auxiliary input is applied through connector J6 and this voltage is regulated down to 5 volts using a 78M05 linear regulator, labeled U1. Decoupling capacitors C6 and C7 each of 4.7 microfarads are placed close to the regulator to maintain stability and suppress ripple. The regulated 5-volt rail powers the logic side circuitry, including the gate driver control inputs and auxiliary electronics. Overall, this section ensures robust control signaling, strong EMI immunity, reliable auxiliary power, effective cooling, and secure mechanical mounting, all of which are essential for safe and stable inverter operation. This figure shows the LED indication circuits used to monitor the switching state of each IGBT in the H-bridge inverter. Each IGBT gate signal is connected to an LED indicator network through a 2.2 kilo-ohm series resistor. This resistor limits the LED current and ensures that the indication circuit does not load the gate drive signal. For each gate, 2 LED lights are used, one green LED and one red LED, connected in opposite directions between the gate node and the corresponding reference node. When the gate drive signal goes positive with respect to the emitter, the red LED turns on, indicating that the IGBT is in the on state. When the gate drive signal goes negative, the green LED turns on, indicating that the IGBT is being actively turned off. This dual LED arrangement provides an immediate visual indication of both turn-on and turn-off states, which is especially useful during initial testing, debugging, and verification of the gate drive signals. Because the LED lights are referenced to the respective emitter, the indication accurately reflects the true gate-to-emitter voltage, not just the logic command. Overall, this LED indication scheme offers a simple, low-cost, and very effective diagnostic tool, allowing quick confirmation that all 4 IGBTs are switching correctly and in the intended sequence. With this, we come to the end of the circuit design part of the inverter. In this section, we have covered the power stage, the gate driver circuits, the isolated power supply generation, the control interfaces, and the diagnostic LED indicators used to monitor the switching state of the IGBTs. Each block was designed with safety, noise immunity, thermal reliability, and practical testing in mind. At this point, the schematic design is complete, and all the functional building blocks required for a high-power H-bridge inverter are in place. In the next part of this video series, we will move on to the PCB design. We will discuss component placement, current loops, gate drive routing, creepage and clearance, grounding strategies, and thermal considerations that are critical for reliable operation at 400 volts and multi-kilowatt power levels. So far, everything we have discussed was about what to design. Next, we will focus on how to implement it correctly on the PCB. Thank you for watching, and let us continue with the PCB design in the next video.